Welcome back. And I'm going to continue the little bit of the history of the Amplitude Locked Loop and what we used it for, and maybe even it's being used for something I don't know. But let's continue with the Amplitude Locked Loop and remind ourselves of what it was. Now this is my version of the Amplitude Locked Loop, which has got a filter, a square law, and the input multiplier, a bit like Archie's original, apart from we used the squarer instead of a rectifier. It was his original idea. There's not a huge amount of difference. It's just a little bit easier to get hold of these multipliers that work at reasonable frequencies. And I explained the last time that if you have a set point of 1, and if you have anything with amplitude modulation going into it, what you get out of here is a constant amplitude. In other words, it strips the amplitude modulation, amplitude variations from it, and out of the filter, and in our case it's an integrator usually, or double integrator and phase lead to compensate it, you get the reciprocal of the amplitude modulation. You don't get the actual amplitude modulation. So the question was what to actually use it for. To start with, we put in amplitude modulation and we got the reciprocal out and so on, and we recovered the carrier more or less, depending on the gain of the loop here. Depends how constant that is at the particular frequency of the baseband signal. And then actually we went on to demodulate double sideband suppressed carrier, which is almost the same as AM, but you haven't got the 1 part in there. You just multiply these two, so there's no power at the carrier, and we managed to make that work quite well actually, because what happened was we got rid of the hard limiter that's usually used in a phase lock loop, and we put an amplitude lock loop in there instead. But the trouble with double sideband suppressed carrier is that nobody was really using it, so it was something of interest. We wrote a paper on it, but that was about it. It never really came to anything. So what were we going to do with it? So the next thing we started to look at was cochannel interference in frequency modulated signals. What I suppose we were trying to do is what would happen if you had 2 FM stations on top of one another. And this is a problem that's been looked at long time ago. So the carrier frequencies are the same, and you've got 2 different signals. What happens at the demodulator is kind of known, but we were looking at that, and if we could separate the 2 FM channels, at least do something of that order. If one of them has got a slight offset, then it's called adjacent channel interference. As it turned out, nobody was really interested in this problem either, but well, there was one special case of it that people were interested in. So I want to look at that, and I just want to look at this, which seems unrelated, but let's suppose we've got 2 carrier frequencies, and they're very close to one another at frequency omega 2 and omega 1. Omega 2 we'll assume is bigger than omega 1, but if it's the other way around, it doesn't make any difference. You get this typical sum of 2 sine waves or cosine waves or whatever. It looks like double sideband suppressed carrier, like a sort of amplitude modulated type thing, but it's not. It goes to 0, and the phase changes here as well. I think the phase is a little bit different at the 0 crossing, but that's not the point at the moment. So we started just looking at a very simple problem, and that was what happens when you just put 2 carrier waveforms. There's no modulation on them at all, and we put them into an amplitude lock loop and a phase lock loop. Now the phase lock loop one, at least the FM demodulator one, had been looked at back in 1945. An amazing piece of work by Corrington and others really were working on that as well. But let's just have a quick look at how you analyze that. So if you've got the sum of 2 sine waves, how do you add them together is the first thing. Well, you can't actually get sum of two sine waves, or well, you can get the sum of two sine waves, but what I was more interested in was waveforms of this form: a cos x plus b sine x, but that would be actually omega 1 and omega 2 here, omega 1, omega 2t. So again, it wasn't quite the same, but you can combine something like this. It's very basic, by writing it as r cos x minus alpha, where tan of alpha is b over a. Alpha, in other words, is arc tan of b over a, and r is the envelope, which is the square root of a squared plus b squared. So if we apply this method to the sum of two carrier waveforms, we've got cos omega 1, let's say the one that I'm really interested in, I'll call that the dominant carrier if you like, plus m, and m is a scaling factor. It's going to be 0 and if there's no interference, upwards to whatever you want it to be, basically, usually equal to 1 or slightly greater than 1. And we define the difference between these two frequencies. That's omega 2 there is omega 2 minus omega 1. And that's not obviously in this form up here with the sine, but we know that omega d, the difference frequency, is omega 2 minus omega 1, and that difference frequency is this frequency here of the envelope. It's often called the beat frequency if you're dealing with, with audio type things. People can hear the beat frequency, which is the difference between two high frequencies, signals added together. But obviously if we substitute omega 2 in here, we get omega 2 is omega d plus omega 1, and then we get this omega 1t plus omega dt, and still not any better off, but at least we've got omega 1s here, we've got x's here, rather than an x and a y, different arguments. But cos of a plus b, if you like, is cos minus sine, so we can expand that with the usual trigonometric formula, cos minus sine. And collect terms of all the cos omega 1s over here and the sine omega 1s on the right hand side, and now we've got it in that form: a cos x plus b sine x, where a is 1 plus m cos omega d, that's omega difference t, and b is m sine omega, or minus m sine omega difference t. And if we combine them together, then we get an envelope, which is, if you square this guy and that guy, you get 1 plus 2m cos omega difference t plus m squared cos squared, and then you get an m squared sine squared, and that adds up to be m squared, and you get 2m in the middle, so you get that as the envelope. And then the phase is given by arctan of this thing here. You can put the minus outside, I think, because it's tan to minus 1 of minus x is minus tan minus 1 of x. I think so anyway, off the top of my head. So you can write it like this now. So r of t cos omega 1 t minus phi is the combination. Notice there's amplitude modulation. Well, it's not really amplitude modulation, but you've got this envelope, r of t. Omega d is the difference frequencies, and phi is the phase. Okay. So the PLL, or the discriminator as they called it in the old days, modulated output is the difference, is the differentiation of the phase, and the AL amplitude locked loop output is the covered carrier and the reciprocal of the envelope, 1 upon r. So we know mathematically what it was. At the time, I don't think we knew this. We just were doing it with on the oscilloscope. I'll show you that in a minute. If you extend this to where one of them's got FM and the other one hasn't got FM, in other words, it's FM plus a single carrier at the same frequency, then you get, well, it doesn't have to be, yes, it's at the same frequency actually. Then you get this, where the difference frequency becomes a function of time, so you get cos of beta sine omega m is the modulation frequency, and there's a Bessel functions and things, I believe, if you expand those. So you get that kind of expression. To find out then what the how it would behave, you need to differentiate the phase, and if you differentiate the phase, you get this expression for the phase lock loop output, where this thing R of t on the denominator, oh sorry, you notice it, R of t squared is the envelope squared of the original signal, because the envelope is the square root. When you square it, it's the envelope squared. Okay, and if you look at this, it's of the form of signal plus signal times noise, and that's a little bit different from what you normally expect in signal processing, which is signal plus noise, and then filter out the noise. So this is like multiplicative noise. You can also look at it as the whole thing here as being noise with a 1 in it, and that's the signal, and then so it's signal times noise. So that's the other way to look at it, in which case the only way it would seem that you can tackle this would be to divide the two waveforms. If you, assuming you knew what this was, and of course we don't necessarily know what that is. So there's the phase lock loop again. So I want to show you what we did. So here's a simulation. So that's just a simulation of ordinary FM. I'm demodulating a signal. That's a transient effect there as I go up. I'm just going to turn that down to 0. So I've basically just got a single carrier. Now I've got a second carrier here, and I'm going to bring that one up. I'm going to offset it slightly so that it's not at the same frequency. And now I'm going to bring it up. And when M becomes 1, they're both the same amplitude. Now you can see the envelope is exactly as we predicted. It's the sum of two cosine waves, in this case, or sine waves. Notice the phase lock loop output has got these interesting spikes which appear as we go past 1. In other words, when the interference is bigger, it flips in the other direction. The amplitude lock loop, this is we actually put an automatic gain control in this one. In the original we didn't have an AGC, so we just scaled things manually with the electronics. The amplitude lock loop, it's a recovered carrier. That's at quite a small difference frequency. Oops, now that's jumped out of lock because I haven't put proper a catch, a sort of software catch on the amplitude lock loop to stop it going into positive feedback when there's a sort of transient effect there. So I'm just going to do this again. So there's our difference of two frequencies, and notice that the amplitude, the integrator output in the ALL has got a similar kind of these spikes, it turns out, occur at the same intervals as the phase lock loop do, and we originally thought, well, maybe we can subtract that away to get rid of these spikes, but that doesn't work, because as you vary the carrier back and forth, if this original carrier gets FM on it, and the ones you put a signal on it. Oh, it's jumped out of lock again. I have to do it a different way. Then you get a rather interesting looking waveform. I'll just do it this way. So now we've got FM. Now I'm going to put the second carrier on, but I'm going to put it right in the center, so it's right on top of the other one. And I'm going to increase it. Now we get an interesting effect when we've got a modulated signal and just a pure carrier interfering. This problem was looked at, as I say, a long time ago. I don't know if I can find. Oh yes, this is the original paper was by Corrington, and this is another. It's about multipath, and he uses a discriminator in those days, and doesn't use a phase lock loop, but that doesn't matter really. And it's interesting that there you go, their signal appears in that paper way long time ago. He worked that out, and he's worked out the amplitude. So all that stuff is quite old. And here's the working out the envelope as well. Although we didn't have this paper at the time. And these are valve receivers. Oh, and there's our signal. That's quite interesting. I don't know why it's appearing on a multipath paper, but we'll talk about multipath in another talk. That's back in 1945. So anyway, this was the problem that we had. We had these spikes. As you get rid of the other carrier, they disappear. As soon as you put the carrier in, there's no signal in the carrier. The spikes get bigger and bigger, and then they sort of flip over in that direction. In the amplitude locked loop, well, the AGC just scales things. The AGC scales everything so it's of a suitable amplitude for the amplitude locked loop, because the amplitude locked loop hasn't got a large dynamic range. So here's the amplitude locked loop. Recovered carrier. It's not perfect because there's transients there. It should be go to 1. I've not put any noise in or anything like that. And there it flips over. How do we get rid of the spikes? Well, Archie was looking on the scope at this waveform, and he said one night, it was about 4 o'clock or something, he says, what if we multiply this waveform by this guy here, the demodulated signal? Do we get anything interesting? I don't know why he suggested it, because it was something I would have thought of doing, but we did it, and you get this waveform out here when you multiply the integrator of the ALL times the PLL, and it looks a little bit, but it isn't, but it looks a little bit like as if you've got the spikes on their own, doesn't it? You see, it's as I increase M. So what we did then, we did it on the scope to begin with, is we just scaled this and subtracted it from this. And what happened? Ah, the spikes disappeared. Well, not completely, but they disappeared. So we had a way of getting rid of these spikes. But when it gets really severe, it was still spikes, but perhaps not as bad. There was always an improvement. Let's see. As I increase I'm increasing the modulation frequency, just trying the same thing. And that's actually much the same as it appeared back in 1980 something, I think it was, when we first tried it, or the late or early 90s. The problem was nobody needed such a thing. There wasn't really a use for that as such. Now we can look at 2 FM stations on top of one another in a second, but just a single FM station with a carrier interference was no good. But Archie, for some reason, thought somebody somewhere might have had this problem, and he went and published this popular article in an electronics magazine, which was the Maplin magazine. And we were sort of laughing at the time, saying, what on earth are you doing that for? You know, who's going to be reading that, you know, of any interest? You know, we were trying to publish in, you know, electronics letters or some of the IEEE type journals, and he was trying to publish in an electronics magazine, but he said, well, I'm interested in real engineers seeing this, and you know, they don't read the IEEE transactions so much as they maybe do a magazine. And I was a bit skeptical, but it's only been published a week or so when we got a visitation from the Ministry of Defence somewhere in England, and they said, we saw this waveform I haven't got the original article, unfortunately, from the Maplin magazine, but it's around somewhere anyway. And we saw it and how you can get rid of it. He says, we've got this problem, not with ordinary radio, but with what's called laser Dopler velocimetry. And what they had was a device which was very similar to what spies use. You may have heard of them in the old days. They would bounce a laser beam off your window, and if you didn't close the curtains, you could actually hear what the person was saying because the window was vibrating. It used an interferometer. You know, presumably these ones were quite small, the ones they had, and there's a technique for that within, you know, if you know about interferometers. But the problem they had was that they were expecting, what they were doing is they were firing this. They weren't firing it at a window. They were firing it at tanks, and from the vibrations of the tank, they could identify whether it was an enemy tank or a friendly tank, using some kind of detection method. You know, they had stored that they knew what these sort of type of spectrum was for one tank versus the other. That's all we knew. But when the laser bounced back off the atmosphere directly due to scattering, you got this effect, where you got these spikes. So clearly it was of use to them because they wanted to get rid of the spikes. And Archie went off and built a device to get rid of them. Not the optical device, but just this device where we had the cancel. Rather, I did, I think, but it was somebody else made it into a thing for the military. I wasn't working on that. And then Fraser Clark, my colleague, there was another kind of polymath really who'd do just about anything. He was an optics expert, and I told him about this thing with the laser. Well, he called it laser sensing, remote laser sensing, where you bounce a laser off something and you get the frequency at which it's vibrating. And he said, well, we can build one of those, and kind of at great expense we did. If I can find the paper that we put it in. Oh, here it is. Well, there's quite a few papers because we had a research student, Olivier Dussarat, from France, who was also looking at the same thing. He did a lot of the setting up of the thing initially, and then made his own contributions later. I don't want to go into how an interferometer works, but this is the block diagram here, various mirrors and so on, and this thing called an acoustic oh gosh, I've forgotten the name now, an acousto-optic modulator. And what it does is it gives you a signal out, which is basically FM, because the laser fires at its target, and it gets the frequency of the target changes the laser by tiny amounts, and those tiny amounts can be picked up by the interferometer. And with this acousto-opto modulator, it's also called a Bragg cell, I believe, and it gives out 100 megahertz, like an IF signal, like FM basically at 100 megahertz. The target we used was in the lab, and was just a loudspeaker with a mirror on it at a known frequency which we could vary. And because it was 100 megahertz, it was a pain in the neck to get it down, because I was working at 455 kilohertz. But fortunately, the same company that published the magazine article, Maplin, I think it was Maplin, had the front end of a radio receiver you could buy in those days. It had no limiters in it. I didn't want limiters, hard limiters. It didn't have a demodulator. All it has was you could, stick an aerial up, and it would give you 10.7 megahertz IF out of this device, little module thing. It's quite big actually. And so I used that. I tuned it in for 100 megahertz, and we got 10.7 megahertz IF out of this with FM on it. And then from 10.7 megahertz, I beat it down to 455 kilohertz with a multiplier which I bought, and then we had 455 kilohertz. All had to be well screened and everything, obviously. And then we went about, again, it was Fraser's idea, Fraser Clark, about how we would simulate the fact that the laser beam was bouncing off the atmosphere and coming straight back. and he did this with graduated glass. Here's the block diagram of the system. It's had a phase lock loop, an amplitude lock loop. This multiplication, which Archie thought of, we scaled it and subtracted it, and sure enough we got the thing to reduce these spikes. But there didn't seem to be anybody really interested in that, other than this military. A week after the British military appeared on our doorsteps, the US military appeared, which is quite a surprise really, considering we're in the UK. And we talked to them, and we told them what we told the UK, because we are friendly after all. And then we told the UK military that they'd been here, and they said, well, what the hell were they doing there? You know, we never told them about it. And they said that the US military were in what's called vacuum cleaner mode or something. They just wanted to know what was going on. Maybe they had something very similar. But the problem we really wanted to solve was what happens when you've got two FM stations on top of one another. So here's one, I'm going to make that 5 kilohertz. Here's a second station. I'm going to bring M down to 0 to begin with. I'm going to put the second station at 10 kilohertz, and then I'm going to bring its amplitude up so it begins to interfere. Now you can see the second station. What was supposed to happen is you wouldn't hear anything, because FM's got the quietening effect. Although some of these frequencies are quite high and you might not be able to hear some of them, you can see it does immediately have an effect when you've got two stations on top of one another. And this does happen, although they space out the radio stations for this very reason. You can sometimes be in a region where you're listening to from one antenna, from one transmitter, and from another transmitter when you're going down in a car or something, and another one pops up. But that might be an identical one, or it could be another station altogether. But what happens, because of the nature of FM itself, as you increase, and once you get beyond 1, the second station comes through. There's the second station, plus all that rubbish as well, of course. So that's the second station we're listening to now. You can put our canceller on, but it does something, but it doesn't do an awful lot. So it didn't really work for 2 FM stations. But nevertheless, Archie, I left the country in the end of 1999, and Archie went ahead, and he eventually managed to have a device which would separate 2 FM channels, him and his co-workers. It wasn't just Archie, but he had people working there. Well, most of the work was due to Archie, I'd say, though, the thinking behind it. But the question really was what were you going to use that for, really? Was anybody interested in that? And the answer to that problem really was not really. Nobody really wanted to separate 2 FM channels, even though he could do it eventually, except for the military again, who came back and they said, oh, that's quite a good thing. And this was the time before the dark web, of course. So I believe I don't know the full details because I wasn't involved directly with it, but I believe what they did was the second channel was be quite at a low level, and it had information on it, and it was transmitted right on top of a normal FM radio channel. So you might be listening to Radio 1 in the UK or whatever, and somebody in a certain area, you wouldn't actually know that second channel was there. But somebody with the right receiver, with Archie's receiver, would be able to pick up a second channel, which would have secret information on it. The second channel would have digital information on it, well, FSK or something, nothing great or anything that fancy, but then they could separate the second channel from the first. So it did have this application in spying. I think the only other thing is in this level, before we go into multipath, is to show that how when you offset the second carrier, you see how the spikes become asymmetric. Again, that was known as well. So there they are. That's when the second carrier is offset, and you've only got one signal. And the canceller still did work for that. But the problem we had with the laser was directly on top, so it wasn't offset by any means at all. So the next thing we're going to look at is multipath interference. By that time I'd moved to New Zealand, and that was the one to crack, because it seemed that industry was really interested in multipath. They weren't that interested in co-channel and adjacent channel interference. They didn't seem to be that interested in whether you put a limiter in or not. Although they were interested, but didn't seem to be of great interest. But multipath was another matter altogether, and I'll talk about that in the next talk.